All right, welcome. I apologize. Welcome to the first video for 8.7, solving radical equations. This is just a typo. This typo should be fixed in your note packet, so you should not have to worry about this. But this is not the videos for 8.6. This is section 8.7, radical applications. No matter when we do the discussion, someone always asks, when are we going to use this? Here's a section that applies to that. First and foremost, classic example, the Pythagorean theorem. You guys know the Pythagorean theorem. Everybody loves the Pythagorean theorem because it's a logically beautiful sentence. It's easy to remember. A squared, B squared, C squared. A squared plus B squared equals C squared. It's one of the most beautiful things ever to be created in math, at least in my opinion. So why would this now apply to radical equations? First off, let's remind ourselves exactly what this means. A lot of people remember a squared plus b squared equals c squared, but they have no idea what a, b, and c are. So it's a useless remembering. A and b refer to a right triangle. That should be here. A right triangle, A, B, and C. A and B are the legs of that triangle, in other words, the sides, and C is the hypotenuse, in other words, the longest side. Some mathematicians say A and B would be the sides of the rectangle created by that triangle, and C would be the diagonal of that triangle, if you want to remember it that way. But it does have to be a right triangle. From last year, you might remember an adaptation of the Pythagorean theorem using trig that would allow it not to be a right triangle, but for just the classic a squared plus b squared equals c squared, you would need a right triangle for that to work, meaning you had a 90-degree angle. Let's go work with this now and see how radicals apply. Given the following triangle, use the Pythagorean theorem to solve for the indicated side. Here we are going to solve for C. Cool. So, according to this, I could redraw that triangle. It looks like this is, in fact, the hypotenuse that I am solving for. So, a squared plus b squared equals c squared. I've got 4 squared plus b squared. I'm sorry, no, 4 squared plus 6 squared equals c squared. All right, it looks like not much solving actually needs to be done here. Let's go ahead and simplify. What is 4 squared? That would be 16. 6 squared is 36. We get c squared. 16 plus 36, somewhere in the realm of, 52, is equal to c squared. Be careful not to box your answer here. We're not after c squared. We're after c. We want c. And so, how are we going to get c squared? We need to square root both sides. C is equal to the square root of 52. If you were doing this kind of math in a geometry class, you were trying to do some of the physics classes, some of the chemistry classes for some reason, you would not want to take this to a decimal of, what is this as a decimal? I don't even know off the top of my head. 7.211102551. You would not want to use that. If you were maybe in architecture, you could use that. But square root of 52 would probably be the most accurate, kind of broken down. 2 and 26, 2 and 13. I might call it 2 root 13. Meters, nanometers, light years, whatever you're working with. I would call it 2 root 13 is the most accurate. Alrighty, let's do it again. We've got over here square root of b. I'm sorry, we've got this problem b, not square root of b. We have a triangle. This triangle is not sitting classically, but we can still see that it is a right triangle. It's floating, kind of hanging out on its hypotenuse here. Let's double check where we are and what labels we would give these guys. Indeed, this is a leg, that is a leg, and this would be the hypotenuse, because if I make this into a rectangle, not a very good one, but a rectangle, we see that the 15 is the diagonal. Alrighty. And so what we have, a squared plus b squared is equal to c squared. I don't want to fill this in as 15 squared plus 12 squared. I need to make sure I match according to the formula, right? We don't want to plug in the numbers to formulas if they're not plugged in correctly. So we've got 12 squared here plus b squared is equal to 15 squared. Now I'm going to go ahead and do some solving. I'm going to move that 12 squared to the other side. Okay, so that's squared minus 12 squared, and that would end up getting us 225 minus 144. In other words, we get 81, and the square root both sides, we get that b is equal to 9. Okay, that is a beautiful number, right? We get a whole number out of this one as opposed to the last one. We get a radical. What this is called, this kind of triangle actually has a special name. It's called a Pythagorean triple. If you're interested, the original Pythagorean triple was 3, 4, 5. The very first triangle, right triangle, that was discovered to have whole number sides and be a right triangle. That's one of Pythagoras' very first things. If you look at our triangle here, each one of those sides has simply been multiplied by 3. 9, 12, 15. 3 times 3 is 9, 4 times 3 is 12, and 5 times 3 is 15. So this is just a triple-sized triangle of the original Pythagorean triple. And it actually works mostly with all the Pythagorean triples. This is a very cool subject to elaborate on. If you ever get into that in an advanced math class, it's very, very cool because you find it a lot in nature. Anyway, all right. The next one, a little more applied to 2020, 2021. We've got police and skid marks trying to get people to stop crashing their cars. Example 1.2. Police use the formula velocity of L, velocity of length. Now, you may not know that yet, but it says V of L is equal to the square root of 20L to estimate the speed of a car in miles per hour based on the length, L, in feet of its skid mark when suddenly braking on dry asphalt road. Of course, if the road's wet, it's going to be harder to brake, right? Maybe it's a little bit bigger, square root of 50L, right? But basically, we're looking at a skid mark left by the brakes. How long that skid mark is can tell us how big the speed of the car was, or how fast the car was going. At the scene of an accident, a police officer measures a skid mark to be 106 feet long. Approximately how fast was the car traveling? All right. Remember, with any word problem, with any problem really in life, with any time you're given a formula and you need to solve something, you have to think about, what do you want and what did they give you? Here we see one number. We see a number of 106 feet long. That was the length of the skid mark. So was that an L or was that a V? There's two variables in this equation here. Are we talking L or are we talking V? That's the question. This looks like to be feet long. I'm going to go with L. So they gave me an L. I can double check myself by saying, okay, what was the question? Approximately how fast? That was a speed. The speed would be velocity. That isn't, oops, no question mark. That is what I'm searching for. So they gave me an L. I can write that L is equal to 106. V is equal to question mark. And now I know what to do. I need to take 106 and I need to plug it into my equation. Remember that this is just function notation, so writing V of 106 does not do anything except tell you that 106 is plugged into the problem. 20 times 106. We can crunch that in a calculator real fast. Square root of 20 times 106 is 46 point. Let's go to one decimal place, 0.04, or two decimal places, pardon me, miles per hour. That is how fast they were traveling. 106 feet to stop, and they were only going 46 miles an hour. That's insane. I usually drive like 60, 70, 80 on the freeway. Imagine if this person was on the freeway. It would take so long for them to stop. Oh my goodness. Okay. All right. One of the people involved in this accident says that he was traveling 49 miles an hour when he braked. If this was true, how long in feet should his car's skid mark be? So this guy is trying to say, no, maybe the speed limit was something weird and it was like 48 miles per hour, right? And this guy who was involved in the accident says he was going too fast, right? You're going too fast. You're going 49. How can we help this guy? So we got 49 miles per hour. Which one was that? Is that a velocity V or a length L? That sounds like a velocity V to me. All right, so we're going to use velocity V. Just double check how long in feet. In fact, they do want an L. So velocity is equal to 49. They want an L. And this whole process of identifying your variable might seem a little silly, but it is very easy to mix those up. It is very easy to just plug in 49 now. But that's not what we're after. 49 is the velocity, and we need to figure out the L. Okay, so let's go ahead and do that. Square both sides. We get 49 squared is 2401. Divide by 20. His skid mark would actually need to be 120.05 feet long in order for him to have been going way too fast. There we go. There's a little delay on my iPad. Sorry about that. So he was actually not going 49 miles an hour, but notice that's not a constant rate. 106, 3 more miles an hour, and he needed what? 14 more feet? That's a lot. All right. In this next video, we're going to do one more problem. Actually, you know what? We'll just do it here because it's very short. 1.3. One way to measure the amount of energy that a moving object, such as a car, possesses is by finding its kinetic energy. The kinetic energy, EK, maybe we can see why they chose that, energy of kinetic, measured in joules of an object depends on the object's mass, m, measured in kilograms, and its velocity, measured in meters, and can be written as V is equal to the square root of 2ek over m. Now be careful here. Remember, when they defined this, EK was one variable. So we've got 2 times EK over m. Right? Don't read this as like 2e sub k, because then you might think there's something to do with an e and a k, but there isn't. This is an ek, and there's an m, and there's a v. All right, what is the kinetic energy of an object with a mass of 15,000 kilograms, and that is traveling at 30 meters per second? Okay, so there's a few more variables here. I want to make sure I know exactly what I have and what is being asked of me. So over here, this looks like a mass of 1,500 kilograms. I think that's probably an M. The 30 meters per second sounds like a velocity to me. Just to double check, it should be the case now that the only one left, EK, is what they're asking for. So let's go look at that. What is the kinetic energy? Kinetic energy is the EK. Okay, good. So that is the one that they are asking for. That is the last one. We've identified these correctly. Let's go ahead and plug this in. 30 is equal to the square root of 2 EK over 1,500. Looks like we are going to need to solve. Sorry, there's a large delay on my iPad from my air server here, but there we go. Square both sides, you get 30 squared. So 900 is equal to 2 EK over 1,500 times 1,500 to the other side. Oops. Whoa, goodness. Okay, we get 1, 3, 5, and 4 zeros. That would be 1,350,000 is equal to 2 EK. Divide by 2. The kinetic energy is 675,000 joules. I'm going to throw a J on there for joules. Wow, that's a really large okay. Sorry about that. While that catches up, notice how no matter what we're talking about Pythagorean theorem in a very theoretical conversation of triangles, or we were talking about police cars and, accidents and scenes, or we're talking about science and kilograms and kinetic energy. The rules of math did not change. The rules stayed the same. The moves for solving were always the same. If I had a square root, I squared. If I had a divided by, I timesed. If I had a times, I divided by, right? It never changed. I just needed to identify which variables I had. Remember, the world bends to math, not the other way around. Now, I will see you again in next chapter. This is now the end of chapter 8, and that will probably happen next quarter. So I will see you again next quarter.